So let us continue with the biasing concept for the active antenna. And that is the concept that we have discussed. It is not the concept with the differential input stage. We'll leave that up to you. This is the concept in which we had the current mirror. I hope you remember it well. So, and here you see the total schematic that we have now. So let's discuss the parts of it. The wait, the input stage here. The input stage. There was an input stage, and maybe you remember the current was measured in a current controlled current source. Oh, that will be a funny one, but okay. A current controlled current source. And that was done because we needed an inversion in the loop because we basically had two common source stages. One was a complementary parallel one, so a P in an N device. So for small signal, I can do it in this way. And then we had, of course, here the load, the two 100, the 250 ohm resistors together making a 100 effective load for the output. This was the output to be measured. And we had, of course, the feedback capacitance going to the input and the source, the capacitive source. And let's say you see the controlled source here for the gain of the antenna, but if I omit it, you can just do it like this. So this was the signal flow diagram, and we ended last time by discussing the bandwidth of this and the stability of this amplifier. And we found out that with a phantom zero in the form of a resistor in series with the input, we could make the thing um, stable and give an MFM characteristic, a little bit influenced by if we are going to use real transistors for this current mirror, because then we have a contribution of the capacitance of the current mirror. So we have a limited FT and we introduce another pole. That is what we did. And here in this schematic, you see there is no decision how to make the current source, the current mirror, sorry. And here you see the current mirror is made with P devices. We could also make it with N devices, but when we do then a kind of folded construction, and that would cost us more current. So here you see it with P devices, and the P devices should be designed such that their GM is much lower than that of the N transistor in order to get a low noise contribution. That is already what we have discussed uh, during the course before. So, but now we have to add, of course, the bias sources, and here is the bias source for the first for the current mirror. So this one is simply shorted, and how it is biased I will discuss later. The first stage, how it is biased, I will discuss later, and then we have the current here, and here is the this part is the push-pull stage, biased with two voltage sources. One of them is controlled by with a gain of one, with to take this point exactly in the middle, but this is not really necessary here. But I just left it in how we designed the stage. I didn't do much about the change of the transistor. I just took the values that we found from the optimum from the previous calculation. And you see here is the 1.8 volt power supply, and here should be a voltage shift of about zero point 0.9 volt, because I want to bias this one in the middle of the power supply just to give me the largest possible voltage swing. Well, this 100 nano farad capacitor is a battery for a short time, and this the voltage across this one will be 900 millivolt. This is called, of course, just simply AC coupling. Now, how to bias the input stage? The input stage, we could say, okay, this transistor M5 needs 1.5 milliamps. So let's tie a resistor to another to another transistor that is exactly the same transistor operating on 1.5 milliamp, the same geometry, and putting there a copy of the gate voltage. That would be model-based biasing, very well possible. We can also say, well, since there is now negative feedback and the whole thing is an amplifier, I can use this amplifier also for controller to be a controller of negative feedback biasing. And that is basically implemented only by means of a resistor here. You could say this one implements a voltage controlled current source that applies here to the input of the FET and gives the correct setting so that the output voltage will be 900 millivolt. And you see it is tuned. And since this gate voltage doesn't need to be 900 millivolt, I need a difference. And this voltage, this level shift is setting this difference. So you see, in this circuit with biasing on what we call concept level, I have still floating voltage sources, one here for the class AB stage, and one here for the feedback biasing, and their implementation, of course, will be discussed next time. But this is what we think is like concept level biasing, ideal sources, minimization, so that you are ready for implementation and for setting up specs of these sources. That is basically the idea. What did I want to tell you more? Yes, if the temperature changes, then M5, of course, needs another VGS. And this other VGS, that is not provided for. That means if the voltage here is not 666 millivolt, or if there is a little bit different device, then the output voltage will not be 900 millivolt. So this is definitely not the best solution for biasing. You could even think of making this source somehow controlled by means of measuring the output voltage, comparing it with zero point 0.9 volt. But you can also see, probably already, the advantage of using a differential input stage. Because with a differential input stage, the gate of this FET and the gate of the FET that you are going to use for anti-series will be on the same voltage. And you can just use that at zero point 0.9 volt and everything will be much better defined. So this is maybe not the best solution of the amplifier. We left the best solution for you and give you the honors at the end of the course. But this is a solution, and we have designed the noise behavior, we have designed the bandwidth and the stability. We could not check the linearity. The only thing we have done was we have designed the output stage so that the drive capability of the stage is large enough so that we know we can handle the signal that we need to handle. That is what we have done. And if we now have a correct way of biasing, and you see already the numbers, the results from LT-SPICE are in it, so it looks promising, everything appears to be biased, then we can do our first simulation of the weak nonlinearity of the distortion. But before we do that, we want to check if the rest is okay. Is the amplifier stable? Is the bandwidth as designed? And is the noise as designed? Because at this level, we don't expect any change, except, for example, for this 500 mega ohm resistor, which is of course noisy, and its equivalent noise source can be drawn like this, a current in parallel. It can be split to the output of the amplifier, which is then in parallel with another. You can forget about it, but it is a current source in parallel with the input. So then we can omit it. And this one generates across the source impedance C3 a voltage, which means that the current noise causes a ramp up of the voltage noise for low frequencies, and not like 1 over f. 1 over f would be like this, but like just normal 1 over f squared for the spectrum in volts squared per hertz. And this point, of course, should be low enough. So this sets a noise requirement for this resistor. This is the only implementation of biasing that I did in this schematic. Basically, conceptually, I should replace this resistor with a voltage controlled current source in parallel with the gate. But because the gate does not accept any voltage, it would immediately result in not finding a stable operating point for the amplifier because of convergence stuff. So because there would be an infinite gain. So I've just implemented it with a resistor.